Hello. I will be talking about the rotary embedding, rotary positional embedding. I went through few YouTube videos and few documents. To be honest, I didn't like most of them. So the way it has been represented is really complex, but in reality, it's not. Uh, so we'll write some codes here and we'll go like one by one and like try to just explain the rotary positional embedding concept, and we'll be fine. So what is embedding? So what is embedding? So when we train in transformer model or attention module, we just give some text. Obviously, the text does not fits in the neural network module. So we convert the text into tokens and the from tokens to embeddings. So we can take an example. So if we take if we consider a text, so like the man is walking. Okay, so this is a text, and then we convert into tokens. So tokens can be tokens are generally numbers or like digit, you can say, that falls between 0 to like vocabulary size. So if we consider the vocab size, okay, for our purpose, let's make vocab size 25. But generally the vocab size is huge. If I talk about llama 7 billion, the vocab size is around 32,000. The vocab size is exactly 32,000. And if we convert the text into tokens, so generally we convert subwords into tokens, but here let's things make simple and we will convert the text each word into tokens. So let's take some random value, so like 10, 13, and probably 7 and 20. Okay, so now each number or each digit of the tokens can be represented with some array of numbers, and that array of numbers is called embeddings of that token, means that corresponding word. So how do we find the embeddings? So let's first convert the tokens into torch.tensor tokens. Let's import some libraries first, that will be useful later. So once we converted the tokens into torch.tensor, we can convert the tokens into 100 vector. So the minimum value is 0 and the maximum value is the vocab size. So here the vocab size is 25 and we can convert the tokens into 100 vector. So tokens 100 is to F2. It is tokens and num classes is basic vocab size. Yep. And if we just visualize the tokens and the 100 tokens, let's see how it comes. Yeah, so we can see so the length, we can see the length is 25 and only one element is only one position. So basically for the first row, the 10th position or the 11th position is 1, other position are 0. Similarly for the second row, third row, and fourth row. And we'll just consider one weight. Vocab size. And okay, so what should be the size of the embeddings? That depends on us. So let's make it 4 as of now. Yeah, and we can have the like embeddings now. basically x, and that like dot product with the weight. And we can make it embedding is, oh, sorry, not x, it's actually tokens, honor tokens. What is happening? Oh, not float type. Okay, so you have to convert this into float. Yeah. Yeah. So we can see now that like each array or each row represent one token, means one word in our case. So each row represent one token. So this row can be like as small as one and can be like as large as like what we want. So for Llama 2 model, it's like the size of one row is 4096. And these numbers represent one token. Obviously, these numbers are not, these numbers are just some random values. And these are data dependent. Once we'll train the model, these numbers will be updated. And at the end of the training, we'll have some final numbers, and that final numbers represent that particular token. So we already got. So now we know what is embedding. So why do we need positional embeddings? Uh, So positional. So when we give some input to the neural network, so neural network consider all the combination of the words similar. So it doesn't make any difference between these two sentences, between these two text. It doesn't make any difference between these two texts, and eventually after training it will produce some garbage that doesn't make sense. So you want neural network to learn some way that whenever it will produce some results or it will generate some text, it has some meaning and it has some like grammatical. We don't want to get some garbage. We want to have some meaningful text at the end of the training or when we generate the text. So if we don't give any positional information to the neural network, so the neural network will consider text and text one similar. So that's why we induce positional embeddings. So it knows in which order it should generate the text. So what are the types? What are the different types of embeddings? So there are like two types basically, like absolute positional embedding, relative positional embeddings. I am not going to talk about them. And there is another type that just combines both absolute and relative uh, positional embeddings. So in this video, here basically I will be talking about rotary positional embedding. That is the famous one people have been using. And in paper, I think the math is complex. People will not. I think I didn't understand in one go. So I think there is like so I found out some like better solution. So we don't need to go through the paper anything. If we know like one basic idea from 10th or to 11th standard, I guess. So we know how things are happening. So if you just rotate a two-dimensional vector with some theta angle in anti-clockwise direction, what do we do generally? So we, yeah, so that's what we do. So when we can go here. So when we want to rotate x and y, there's two-dimensional vector in anti-clockwise direction by theta angle, and eventually the resultant will be x prime and y prime. So we just take dot product of the like matrix cos theta minus sin theta cos theta with the existing vector, and we get the resultant. So, this is the only concept we need in our case. So if we know, we just need to we will like apply this transformation for all the like two-dimensional vector in the qx and kx. We'll be talking about the qx and kx, and then we'll be good. So let's talk about what is qx and kx. Before that, before talking QX and KX, before before talking QX and KX, I'm not going to use this embedding, the previous embedding, this one. because I want to make sure the like the things we do and that can be directly applicable to the like fine tuning or pre-training large language model like llama or other things. So I'll consider all the like batch number, sequence length, number of head, and the head dimension. So let's consider something. So let's take a like random value. Let's take a random tensor x. So that is the input. So basically, you can think about x embed is the basically embedding. This is the embedding, and we are just talking random. So what is b, t, and c? We can talk. We can just write. So b is basically batch size. T is sequence length is, and C is the embedding size. For llama 2, it's basically dimension in llama 2. Dim in llama 2. Llama 2. Yeah. So we have embeddings, and so this embedding we'll be considering for the following talk. And then what we can do, what we have to have some Q and K parameter. And what is Q and K parameter? This is basically query parameter and K is key parameter. And what is Q and K does? So Q basically query means like what we are looking for. K means what we are containing of. So we do the dot product of Q weight with the embeddings, and we get some the query of the input. And similarly, when we do the dot product with the K weight and embedding, we get the key of the input. So basically what previously I'm looking for. So whenever we take some dot product between like query and Q values, so the dot product is basically gives the best possible combination that like what I'm containing and what I'm looking for. And if the dot product in some position is the maximum, then that means like for all the previous things, I want this maximum case. So once we have, if we just take the dot product between Q and K, then we'll have like this. Yeah. Oh, sorry. This is embedding actually. Now let's see the shape of Q, X, and K. What is okay? So now so this is not the input generally we consider. So we again reset Q, X, and KX. Now introducing another variable that is NH. So NH is basically the number of head. Change is the number of head, and now we are introducing that, and we are just reshaping the QX and KX. It is like batch sequence length, that is T, NH number of head, and like C by NH. Now, obviously, now the shape will be like this. Okay, now as I was talking previously that we want to rotate a two-dimension vector with some theta angle. We'll see that how we are getting the theta, and but from here QX and KX we can say that how we what we need to actually like rotate. So if we talk about the large dimension, that is basically the head dimension we call. So head dimension we call the 8. So in head dimension, we convert this large dimension, we make groups, we make some groups such that each group has only 2 elements. So each group is basically a 2-dimension vector. And that 2-dimension vector, we want to rotate by some theta angle, we don't know yet, using the transformation matrix. So that's our purpose. So okay, let's just convert the matrix and probably let's reset the matrix again. As I was talking. So see, so here 4, 16. So that's batch dimension 4, T dimension 16. Number of head is 4, and again this is the 4 and 2. So that last 2 is like one 2-dimensional vector, and so that vector we want to rotate theta anti-clockwise by some theta angle anti-clockwise in anti-clockwise direction. Okay. So now we are done. Now okay, let's see the how to compute the angles, and basically then we'll see how to how to transform or how to rotate this embedding vectors. Not embedding exactly, it's like the head dimension vector and the head dimension side axis. Okay, to compute the angles, it's already given in the paper, and also it's given in the like Llama 2 code. I took it from there, but I think and I changed it little bit. Basically, there is another line after the angles, and I didn't do anything. And I like removed the line. We'll see later what I did, what I removed. So what is happening basically here? So we have some tokens, and tokens has some position. So if we start, the man is walking. So the like da is in the 0 position, man is in the like first position. So something like this. Like start from 0 and it goes till t minus 1. So that is the absolute position. 0, 1, 2, like t minus till t minus 1. And that is the absolute position. And that has been represented by the m parameter, sorry, m variable here. And there is another direction. So this is the t direction. There is another direction. So that is the head dimension direction. This direction, head dimension direction. So what do we do head dimension direction? We just because basically we convert as we convert two elements from the head direction, we want to rotate them by theta angle, some theta angle. That's why we consider like d by 2 dimension here. So we go till like head dimension by 2. So here it's like t dimension, here it's like head dimension by 2. And that head dimension by 2, these angles we get from the theta, this theta. And that is given on the paper. So here like head dimension by 2, and in this direction like t. So if you just take the outer product, so and we'll get all the possible combination of like head dimension by 2 and t, and that is the angles here. So this angles, so for if we talk about, the first head dimension by 2 and the first t, that means so then if we take the just like one values like first head dimension by 2 and first t, that's like zero positions, we'll give some, like if we just multiply, because both are scalar, if you just multiply we'll get one value, that is so like one angle that will transform, or that will rotate the qx or qx in the very first position, Okay, so basically let's see how will we do. Let's see. We can see that. Okay, so we can see, we can just take angles dot 0, 0, 0 and 0. So this, okay, let's make it 1, because basically it first start with 1, so that's why it's 0, 0. So okay, that's why it's 0, and let's 0 0.10. So this angle will basically transform or rotate. Where is qx? I think, yeah. 1 1, right? Or if we just make it 0 0, I think it will be better. So we'll take everything 0 here. 0 0 0 0. I think 0 0 0 0, and yeah. So yeah. So this angle, yeah. So this angle 0, this will basically, so we want to rotate this vector. We want to rotate this vector with this angle in the anti-clockwise direction. With 0 angle in the anti-clockwise direction. Obviously here it is 0, but if we talk about like 1 and 2, here I think some number will be changing, but I think it's 0, doesn't matter, the best dimension. Here is t dimension means 1, and here again it doesn't matter. I think here it will be 2, I guess. Just let me see. It is 4. 4 means the head dimension, that is, yeah. Okay, so this vector, we want to rotate in the anticlockwise direction by 0.01 angle. And now, so what do we do? So there is like one way just generating, just take a matrix. So matrix will be like how? One matrix will be, okay, so first is the tensor, and let's make like angle, angle, and this is the vec. We know angle, we know vec, and how can we transform this matrix? So we'll just take the, like, okay, rot, row matrix, rotate matrix. Mat is basically, I think will be like okay, torus dot cos minus torus sine, like dot is angle ANGLE, and then similarly minus TRCS torus dot sine ANGLE, and we'll go here again TRCS torus dot I think sine angle and torus dot cos torus dot yes angle. Okay, then go mat. Okay, and now we have to, so you can see this is good because the corners elements will be equal, but when we will be talking about the sign, it will be just so like sign corner, it will be thus like plus and minus. And now if we just see the result, rotated vec, and that is basically that's all, the row mat and the dot product, and the dot product is basically vec. You can rotate, you can bring this, sorry. Okay, so yeah, so you can see, so we started with one vector, that is the vec. So this is this, and we want to transform, we want to rotate it in the some theta angle, that theta angle is 0.01 in the anticlockwise direction. So after rotation this vector, after rotation the vec vector with the angle, and we get this rotated vector that is like 3.371 on and this is what we just need to do for all the elements belongs to the QXRE and yeah, KXRE. That's the only thing we need to consider. Uh, so now let's as we know the shape of the angle is 16.4, but shape of the QXRE is like 4, 16, 4, 4. So obviously there is some mismatch of the shape, and that we know why it's happening, because where we are getting the angles, we are just getting the t dimension. Basically this is the angle shape is will be basically t, sorry, t, and let's make it h's here. H's, what is h's? H's is basically by nh. Yeah, so t and h's we have, sorry, h's by 2, h's by 2 we have, yeah. So, but in the before and but for b, what do we have? So let's make it here. So we have, sorry, okay, let's make it qxre, I think, dot save. Yeah, so qxre is basically we have b, t, nh, hs. We know hs is basically c by nh, right? So we have hs by 2, and let's just change this to, sorry, yeah, so hs by 2 and here 2, yeah. And we have angles, we have this, we only have like t and hs by 2, yeah, hs by 2. We can see, okay, bring, oh, sorry, okay, did I do any mistake? Oh, sorry, yeah. Yeah, now it's really fine. Okay, so obviously we can see that like in the angles, the base dimension is missing. So that means the 4 dimension is missing, 16 is matching, another 4 is missing, and the next 4 is missing. So okay, sorry, now first 4 is missing. That means the NH dimension is also missing. So we'll just repeat them in those dimensions. And this is how we do it. So first we unskews in the like 0 dimension, that is base dimension, and the 2 means in the NH dimension. And once we have unskews, we can see the size, and we just repeat them in the like with the B and NH. Yeah, now we can now we can match the size of this. Sorry. Oh, okay. I think we cannot take more than one rotation. I think because it's updating, keep updating itself. That's why the problem. Okay, now we can see there is a match. So see, this is the angle. So the first one, this is the angle. So it's the batch dimension is matching, time dimension is matching, NH dimension is matching, and the HS dimension is also matching. So now we have this 2 dimension left. That 2 dimension will be converted with this like only one angle. And we can do this. They just simple. Let's convert into let's find the cos value. So cos angles will be dot cos the angles, and sine dot sine angles. Okay. Once we have them, we just can just see how it is. It's just like same shape, sine angles. Okay. Oh, sorry, angles. And, yeah. Okay. Okay. So once we have them, we can see some just like it will be the same shape as before. Now what we need to do, we have now cos and sine. We have like cos and sine separately. Now what we want to do? So if we want to make like matrix of that, like the transformation matrix, so the top left corner will be cos, the top right corner will be minus sine, and the bottom left corner would be sine, and the bottom right corner would be cos. So it's basically cos minus sine, sine, cos. So that is how it is, right? So we can make it. So we can make it. So we have to expand this cos and sine into 2 dimension more, because that's where it will be like concatenated. So we can do it. Opened it. So we open another dimension, like the last 1 and 1 dimension. So here this will be the concatenation. So we can concatenate. This is not. So this is like cos sine 1. So that is the top layer. So top layer, that means top layer. When we are concatenating top layer, means we are like taking the cos and minus sine, right? So that means that means they are concatenating in the column dimension. Column means row into column. That means large dimension. That's why we get the -1. So we already got, and then we'll concatenate in the same thing. There is the, so the first one, the cosine one is the top layer, cosine 2 is the bottom layer, and they are concatenating over the last dimension, that is the, or the like last matrix column dimension, that is the -1. And once we have them, we can again see the shape. Yeah, so see, they got concatenated over the last dimension. Once we are concatenated over the last dimension, we can just concatenate. Now we have the top layer, bottom layer. Now we have to concatenate like this in the row dimension, right? Row dimension. So row dimension means the second last dimension. Yeah. So now we have everything. So we started with, see, now so we started with 4, 16, 4, 4. So that is the like angle shape. And for each angle, we have like 2 by 2 transformation matrix. And that transformation matrix will transform that the QX on KX, the 2 dimension of the QX and KX, the last dimension. We'll see how to do that. Let's see how is the shape of the QX and KX, and from I think from there we'll move. We can. It's right now. Let's see. Okay, so we are matching in the first batch dimension, second the T dimension, third is the number of head dimension, that is NH, fourth is the HS dimension, that is head dimension. Sorry, yeah, head dimension or head size we say sometimes. This one is also matching. So this is like 2 and 2 because we need to do dot product. That's what we are talking about. But here it doesn't have one dimension, so we'll just expand this into we'll expand QX and KX into another dimension, that is the last dimension. So I'll just unsqueeze in the file and you can see the shape now. It should be fine. Okay, and once we have, that's all. So we are done. So if we just need to take the dot product, nothing else. So if we take the dot product, so we have rotation matrix, and we are taking dot product the QXRE. So what is happening? So like BT and HHS 2 2, so that each 2 2 is getting dot product with the each 2 1, and other dimension are same. So the type will be like BT NHHS 2. So now it's done. And how it will go, we just want to kill the last dimension because it doesn't make sense. It is just one. And once after killing it, we'll just make it as we got the input, basically the QX. So this is how we want to see. So now we are done. So this is the 41648 or like BT NHHS, that is how we get input, and that is how we give the output if we make it function, but we are not doing. Now one thing, like we can have a question like, okay, we did something that is just like simple one idea, and that is coming from here, only just transform or rotate the two-dimensional vector in anti-clockwise direction by some theta angle. But how will you verify that this is correct or not? So for that, I have taken some code from the Llama 2 model, and I'll just go through that code. So this is the code. If you want to check, I think you can check. I have just copied from the Llama 2, and this is the code. So basically what you're saying, it's like pre-computed frequency CS. Okay. So this computes the angle till this position, I think. Yeah. So till this position, my code is same computing angles. So after that, they just convert it into some complex number. To be honest, I didn't like that. It was not needed, I guess. And I felt like the way I did that is more easy. And once they just applied the rotary embedding. So we can apply and see what is happening. So let's see. So we just take everything same. It is like their angles. So we just give HS and T, same thing. So they will calculate the angle from this. It's like the complex angle because this is the torch polar output. And once this will have, we'll just apply the QX coming from the previous, like from beginning. And the same QX I used, and the same QX they will be also using. And we have, okay. Oh, I think I have not run this code. Okay, now it's good. So now we can compare whether this is good or not. So let's just compare. Torch.all close. It's like this one and ours, right? Rotated QX and up. See? So we can see, like, even we can print that, yeah, this is good. We can print this. So see, so like they did some complex. Even I didn't like this also. Here they've converted into complex. I thought it was not needed. It wasn't. But again, I think it's like just view. I understood in that some simple way. And I really found it hard to understand in this way. So both are matching. And we can print some of the values and we can see what is happening. See, everything is same. We can probably see something here. Yeah, we can do something here also. Yeah. So both are things. So that's all, guys.